Hello guys again. Let's work this second frame for the series of videos in structural analysis. Now this frame, in the previous video we did a frame with perpendicular members, that was it. And now we have this inclined member, and I brought this particular problem because of that situation. I want to teach you and I want to show you how that is taken into account. So once again, first thing first, reactions. I didn't put letters here, but let's say that this is A, B, C, D, E, F, G. Okay, so this is gonna be dy, and this is gonna be AY, and this is gonna be AX. Now the first objective, the first thing that we have to do is calculate the reactions. If I do summation of forces in X, that means that AX is 0, and we are done with that. Now for doing calculating the reaction dy, I'm gonna do summation of forces at AY. So this is a rectangular distributed load. Is gonna produce a constant. No, it's not gonna produce. It's gonna be equivalent, for the sake of calculating reactions, of having a concentrated load at this point of 12 times 2, 24. We put here 2 times 12, 24 kilonewton at that point. So let's do summation of moments about point A for calculating our reaction at D. If I do summation of moments here, I have 10 multiplied by 3 negative. Remember, put my pin here, I apply the load, rotation goes in this direction, that direction is clockwise, and we assume counterclockwise as positive, so it's going to be negative 10 times 3, and then I have dy, pushing it up, assume that it's pushed up, dy plus times 6 plus 6, and then minus 24 times 6 plus 6, and that has to be equal to 0. When you solve for dy, you're gonna get something, I don't know what. Let's see what we get. This is 24 times 12 plus 30 divided by 12, 26.5. So 26.5 kilonewton. You see, people complain that I work with units in the USCS system, American system, but these are SI units, so don't complain. Now I'm gonna have people complaining because I'm using SI units and not imperial units or American units, USCS system. Summation of forces in Y equals 0. So AY minus 10 plus dy minus 24 equals 0. 34 minus 26.5, 7.5 kilonewton. There you go. Now what is the next step? Let's see if you watch the previous video. What is the next step? I'm gonna make a poll right now. Raise your hand. What is the next step? I'm not hearing you. Review your reactions. Verify, check your reactions. Even if it's in the calculator, you don't have to write it. You can do summation of moments at point C, for example, and put every single value that you have over there. So if I do summation of moments at C, let's see what happened. I have AY 7.5 times negative, right? Times 6. I put the negative here. Negative 7.5 times 6 times 6. Okay, negative 7.5 times 6. Plus AX is 0 plus 10 times 3 plus 30. Then I have minus 24 times 6 plus 26.5 times 6. 0. That means that my reactions are correct. How long does that take? Nothing. But now I'm sure that this is correct, and this is correct. And I have less chances to mess up then. Now, second step was member and forces. Member and forces. Let's calculate member and forces. So let's get these out of the system, which is, by the way, why I wanted to do this. And then I have this 7.5 acting here. And then I have this 10 acting here. And I'm going to need this angle alpha, which is 6 divided by 6, so alpha is equal to 45 degrees. And then I have to calculate the values at this end. The values at that end, I'm going to call them CY. And I'm going to put the moment here as NC. And in this direction, I don't have anything because I don't have anything in this direction also. I'm sorry, this direction. In this direction, I don't have anything because this is 0, AX. Okay, good. Now, if I want to calculate CY, I just do summation of forces in Y equals 0, meaning that CY is going to be 2.5, 10 minus 7.5. And then if I do summation of moments at this point, let's say, this point, summation of moments at C, then I have 7.5 times this distance is 6, 7.5 and this distance is 3, and the height is also 6, so 7.5 times 6 negative plus 10 times 3 plus MC equals 0, and MC equals 15. There you go. But these, if I want to draw my shear moment diagram, then this is not, those are not parallel and perpendicular to the axis. That means that I have to decompose these forces into parallel and perpendicular to that axis. So let's do that. Let me do that here. I have 7.5, and this is the only part. I'm not gonna say that it's complicated because it's not complicated. Let's say this is the part where people mess up the most. And I have this 2.5 here, but I'm gonna keep it like that. So this angle is alpha. I don't need that force like that. I need this, and I need that component. That's what I need, these two components. Now let's study the angles a little bit. And if you can't see it so small, blow it up in a bigger drawing and look at that better. If this angle is alpha, this is going to be 90 minus alpha because this is 90 degrees. That's what I'm looking for. So if this is 90 minus alpha, this angle here is alpha again. Now I can use this angle for calculating my two components. This component, horizontal component, is going to be 7.5 sine alpha, and this component here is going to be 7.5 cosine alpha. Those are the values that I will use for doing my diagram. And you can, the angle is 45 degrees, so it's not gonna, you're gonna mess it up. Although I have seen so many people messing things like that you think it's impossible to mess up. However, they figure and they manage to mess up. This is 5.3. 5.3. Now we have to do the same thing with this force of 10 here. I'm not interested in that force like that. I'm interested in the component that goes parallel and perpendicular to that one. So basically I'm interested in this component and in that component for that force. Now let's study the angles again. This is alpha, meaning this is 90 minus alpha. And I know this is 45 degrees everywhere, but I just want to show you what is the way I approach this problem. So this is 90 minus alpha, and this is 90. Because this is a straight line, this has to be alpha again. If this is 90 minus alpha, this has to be alpha again, and this is 90 degrees here. So what does that tell me? That tells me that if I'm looking for this is going to be 10 cosine alpha, and this is going to be equal to the one that is acting here, which is going to be 10 sine alpha. And how much is that? Square root of 2 over 12.707, so 7.07. 7.07. Now, remember I had this force here. You can put it, the moment doesn't change, thanks God for that. The moment is the moment. I'm not going to change that moment, it's 15. You don't have to rotate the moment because exactly that's what the moment is, rotation. But instead of me rotating this force of 15 that I put here, this force of 2.5, what I can do is I can do summation of forces in this direction. That's what I can do, if I want to. Otherwise I can rotate that. But if I want, I can do summation of forces in x equals 0 in this part, and I can do it perfectly. And I can do 7.5. Now, remember global coordinate system, local coordinate system. This is my coordinate system for this one. For this one, I use this. Now I'm rotating it like that. So if I do x, it's not going to be x, it's going to be with respect to x1. But you know what I mean if I put x or y. I'm referring to this coordinate system and not to the global coordinate system. So if I do that, then this is going to be 7.5 minus 7.07, right? At 7.5. Who say that? You see how that people get errors. This one, 7.5 sine alpha, 5.3 minus 7.07 in this direction means that I'm going to have this reaction in this way, Cx prime, and plus Cx prime equals 0, so Cx prime equals 1.77 or 1.76 something. Let me see, because I use the full decimals for some stuff. So yeah, 1.77 kilonewton. And you can do the same thing with this other reaction here, Cy prime. Summation of forces in y prime equals 0. And if I do that, then you can just come here and say 5.3, this one, minus 707 plus Cy prime equals 0, Cy prime equals 1.77 kilonewton. Now, this is the same because the angle is 45 degrees, but don't get used to that, please. You could have also used this one and converted it here in the same way that we did before. You could use this and say, okay, what I'm looking for is this one here. That one is the one that I'm looking for. And this other one here is the other one that I'm looking for. Pointing in this direction and pointing in that direction. And I can say, oh, if this angle here is alpha, look, it's basically the same thing as this one here. So if this angle is alpha, here, this angle here is going to be 90 minus alpha. This angle here is going to be alpha again. And this value here is going to be 2.5, which is the value that I got before, 2.5 cosine alpha. 2.5 cosine 45 is going to be 1.77. It's the same thing that we did before, but in this case, it's like a reaffirmation. I'm rechecking my work again. So we already finished this enforced member here. So now we can do the other enforced member. Should I use this space here and save a couple of trees? People hate when I do that. But I'm used to be hated, so it doesn't matter. This is the story of my life. Now I'm gonna use another paper. 2. I'm gonna put that member and only that member over there. So here. Should I study the joint? Well, we certainly can study the joint if we want to. This is what we have. But using this part, I calculated this value CY, and CY was 2.5, and the moment that we calculated here was acting in this way. So in this case, meaning if it was acting up, here it's going to be acting down. If it was acting in this direction, now it's going to be acting in that direction. Now going back to this end, this should be like that, and this should be like that. And when you transfer it to this part again, then you're gonna have this reaction acting in this way, and the moment is gonna be acting in this way. That's what happens. It doesn't worth it doing this because we don't have any concentrated forces or moments here like the next example that I'm going to do. But for this example, you just can come here and say, oh, if this is up, it's going to be down here. If this is counterclockwise, it's going to be clockwise here. And this is 2.5. And then you have the rest of these. Two kilonewton per meter. And then you have the force here, the reaction. And that reaction is dy 26.5, and that's about it, because this is a cantilever end. The summation of everything has to be 0 here, otherwise I don't know what we are doing. And you can check it. Look, this is 6 and this is 6. This is 12. 12 times 2 is 24, right? 24 coming down, and you have plus 2.5 coming down is 26.5 coming down, 26.5 going up. Summation of forces in Y is 0. And as well, you can do the other summation of moments, and you're going to see that the moment is going to be 0 no matter what. So this is the second enforced member for that. Now, once we have the member enforces, then we can go and solve for our diagrams. Axial, shear, and moment diagrams. Okay, let's do that. I'm going to keep the members as they were here, inclined. So I'm going to put the member here, inclined. And I'm going to put the other member somewhere here, horizontally like that. You don't have to copy this every single time. I'm just doing it for explaining you while you study. 26.5, and then you have these moments, enforced members. Where are you? I just had you. 15 and 2.5. This is this. Now for the other one, is this one here. So I'm going to have 5.3 and 5.3, these two. And I'm just going to have these two forces here, 7.07 and 7.07. Remember, these two come from this one that was the vertical one of 10. And then here I have these other two forces, which are 1.77 each. 1.77, and the other one is 1.77 also. 1.77, 1.77. Okie dokie, we are good. And now we can do our shear moment diagrams. Okay, let's start with this one. I'm just flipping it, so I can make my point of view like I'm used to. Like that, horizontal and vertical. In the future, you're gonna do it inclined. For now, it doesn't hurt if you just do what you are used to do. Now, axial. Let's start with the axial. You start with a compressive force here of 5.3. Let's say that I'm gonna put compression because it goes to the right. I'm gonna put compression going up. And then, of course, you need a line here. It doesn't have any other axial force up to that point, so we go constant. Here we have a 7.07 pushing it down. There's gonna be compression, pushing it down, and this is pushing it down. It's gonna be up to this point here, so this is gonna be compression, and this value here is gonna be 707 minus that 1.77. There's nothing else here in axial. Go straight, find this axial going up, 1.77, closing 0. Really small, yes, here, because we haven't done much tension. Okay, good. Now let's work with our shear diagram. Shear diagram starts with 5.3 over there, going up, constant all the way. Find now this float, pushing it down, and go to the very end, constant. Find this, push it up. Now you do a bigger yes. And this is positive and this is negative. Now we work with our moment. Oh, look at me. Nice. Moment. I didn't put this moment in the enforced member. I put it here, but I didn't put it there. So, and I realized it because I saw it here. So this one, we have to have that of 15 over there. Okay, good. Now we do our moment diagram. Anyway, we were gonna realize this as soon as we started doing the moment and we go to this point. We're gonna end with 15 that we needed to close it in 0. So what do? 1.77. If we use the method of the areas, how much is this distance? Oh my, I didn't calculate that distance. This is such a big deal. I need to calculate that distance. How much is this distance? Well, that distance is going to be 3 divided by sine or cosine of 45. 4.24. So this distance is 4.24. Oh my, oh my. Now, this is going to be positive constant. That means that we're going to go positive constant up to that point. The moment is going to be positive here. And the values are going to be 1.77 times 4.24, 7.5. What am I doing? Can you please explain me what am I doing here? Why I put 177 here? It's 5.3. What? You guys don't correct me. 5.3. 5.3. This one here is 1.77. And this one here is 1.77. 5.3. This one. Now, 5.3. I'm not gonna edit this because if it happens to me, it can happen to you. And hopefully it happened to you. 5.3 times 4.24 equals 22.5. 22.5 over there, or 22.47. And now we have this negative area here, which is 4.24 times 1.77. And that's going to be negative 15. You see that? Negative 15. I mean, positive 15 here. And then this is going to be constant up to that point also, and we reach that point. Now, once we are at this point, we see this moment, and as I told you all the time, you just, if the moment is like that, you look at the left side is pushing it down, so this is going to bring it down. Now we have a bigger achievement here, so we can make a bigger yes. Remember, this is positive, this is positive. Now we switch to this one. Once we switch to this one, you have this and that, and you have axial, shear, and moment. Let's start with the axial. This is called an axial diagram in 1 second. Done. Axial. There's no axial force. Shear. Find the force. Pushing it down. 2.5. Negative. Then you have this force, which is also negative. These distances are 6 and 6. So it's 12. 12 negative, 2.4, 2.5 negative is going to bring down to 12.5, 14.5, 12, the area of this load, negative, and this 2.5 negative is 14.5. And now we go to this point and we find this force, 26.5, which is going to push it up to 12. 26.5 minus 14.5 is 12. And then I have this other area here, which is 2 times 6, 12, negative, and this is positive, and it's constant, so it's going to be constant up to that point, and it's going to close in 0. Yes. Oh, I didn't put yes here. So it's really small yes. And now we do the moment. So let's start with our moment diagram. Our moment diagram starts with this 15. As you can see here, it's a moment that is pushing up. So it's going to go there, and it's going to be a positive moment of 15. Now I find this negative area. This is a trapezoidal negative area. And that trapezoidal negative area is 14.5 plus 2.5 times 6 divided by 2. So this is basically 17 multiplied by 3. Is 51. 51 is minus 15 is 36. So it's going to be negative 36 here. And this is going to be, this is a straight line like that, but this is an area that is a trapezoid. So that area is something like this, even though you don't see it very well because of the scale that I drew it. It's an area like that. Now I have a circle that I use. Positive decreasing, negative increasing, negative decreasing, positive increasing. That's what this means. And I have a mnemonic that one student created to remember the circle, and it's please don't neglect infants, neglect dumb people instead. And basically we use this to know the shape of that. So if you want to know the shape of the moment, you look at the shear. And the shear, the area is negative definitely because it's plotted below the axis and it's increasing in absolute value as you move from left to right. So it will be negative increasing. Negative increasing is this shape. So that shape is like that. If you want to know a little bit more about this, in case that you don't know, just go back to my static modules, my static libraries, and you can find that. Now you go to this point and you find this is a positive triangle. I know this has to close in 0, right? And if I want to verify, I can. It's 12 times 3 or 12 times 6 divided by 2, the area of this. So it's going to be positive 36, negative 36, 0. But once again, let's try to do the please don't neglect infants, neglect dumb people instead. This area is positive because it's plotted above. And it's decreasing because the absolute value is decreasing. So positive decreasing is going to be something like that. and it's gonna close here. And now, please, by all means, celebrate. Yes, you're closing zero your diagrams. Now comes the deflected shape, and it's the last part that we are asked to do here. Remember, for the deflected shape, you have to study first the type of support and the type of moment diagram. So let's put here our structure. I'm going to put here my support, and I'm going to put here my support. And of course you have all the loads and everything else, which are important. They are really important because they tell you what to do. So you have this load here, which basically you can decompose in two different loads, but you have this other load here also, like that. Now look at the moments. What is first? This is a roller, right? So this structure, because of these loads, because of what is happening here, it might displace to the right. I don't think so. It doesn't have, everything is symmetric. I don't think it's gonna displace to the right. However, this is a pin support. This is gonna suffer a rotation in either direction, but it's gonna be a rotation. And if you look at the moment diagram, it's positive. That means that for this whole area, the shape has to be like that, a frowny face. Compression on the top, tension in the bottom. And for this other area, if you look at this closely, this part is going to be positive up to that point. By the way, you can calculate that if you have the equation of this moment. And you have an inflection point there. Whenever the moment is zero, then you have an inflection point in the deformation in the shape of this curve. So, but this is positive in this part, and the whole diagram from this part is going to be negative. The moment is going to be like that, positive, negative, positive. Now if I have to put everything together, basically what is happening here is something like this. You have this tension happening here in this part, and this is going to be following something like that. But this is a moment connection, so that angle that I have over there has to be maintained somehow here. And this is positive up to this point. Up to this point is going to be positive, like there. And then after that, everything becomes negative. So this is the inflection point. This is going to be like that, positive, and now here it's going to start switching to negative, like this. And it's going to end somewhere like that. I should have done this in a different color so it can be better seen. So this is gonna come like this, gonna come like that, and this point should be a little bit more to this side, but it's the roller should, I mean the point where it's gonna cut here, this part is not gonna move up and down, but the beam can displace through the roller, something like that. Kind of like that, and this angle has to be kind of similar to that angle because it's what we had before. Okay, that's the second frame, and I'm going to be solving a third frame really soon. Keep watching, guys. See you later.